Today we're going to give a combinatorial proof that if n is greater than or equal to p, the n plus pth Fibonacci number is equal to the sum from I equals 0 to p of p choose I times f sub n minus I. So just for example, to see what this is saying, this is saying, like, for example, f of n plus 3 is equal to, well, the sum from I equals 0 to 3 of 3 choose I f n minus I. So that would be fn plus 3 fn minus 1 plus 3 fn minus 2 plus fn minus 3. Okay, so that's an example of what the theorem would say. And we want to show this is true for all n greater than or equal to p. Okay, so just as a reminder, the Fibonacci sequence starts with f0 equals 0, f1 equals 1, and fn equals fn minus 1 plus fn minus 2. And this is for n greater than or equal to 2. Okay? And so the way we're going to prove this is we're going to show that the Fibonacci sequence counts some sort of combinatorial object. So a theorem that's not too hard to prove is that fn is equal to the number of tilings of, okay, well, this is a theorem with pictures in it, of n minus 1 blocks. Okay, it's the number of tilings of n minus 1 blocks made up of monominos and dominoes. Okay, and this follows immediately from induction and the fact that if it ends with a domino, there's fn minus 2 ways to tile the beginning. If it ends with a monomino, there's fn minus 1 ways. So this is pretty easy to show. Okay, if you don't believe me, let me show you an example. So for example, let's say n equals 5. So we know f5 is equal to 5, and it should be, if this theorem is true, there should be 5 ways to tile 4 blocks with monominos and dominoes. So let me draw them out. We could have all monominos. We could have it end with a domino. I think we got it. Okay, you could check. These are the 5 ways of tiling. The 4 blocks with these 2 tiles. A single tile and a double tile. Okay, so we want to prove this theorem. And what we're going to do is we're going to show that the left-hand side and the right-hand side count the same thing. Okay, in fact, what we're going to do is we're going to say what the left-hand side counts, and then we're going to break up those, we're going to partition those objects based on a certain property, and that's going to be counted by the right-hand side. Okay, so the left-hand side, which is fn plus p, we know that's the number of tilings of some blocks. How many of them? N plus p minus 1 blocks, right? That's what the theorem says. It says fn is the number of tilings of n minus 1 blocks, so fn plus p is the number of tilings of n plus p minus 1 blocks. Okay, and so the last p tiles Okay, not to be mistaken with blocks. So blocks are these things here. Tiles are either the monomino and the domino have some number of dominoes. Let's say have some of these, let's say I dominoes, and P minus I monominos. And I could be any value between 0 and P. Okay, so the last P tiles could be some combination, we don't know the order yet, we're going to have to order them, of dominoes and monominos. Say there's I dominoes and P minus I monominos. Say that 2 times fast. Can't even say it 2 times fast. Okay, so how many blocks does this take up? This takes up well, 2 I blocks for the dominoes and P minus I blocks for the monominos, which is P plus I blocks. All right, so this takes up the final P plus I blocks are made up of these I dominoes and the P minus I monominos. And so our tilings here's the final P plus I blocks. The total was N plus P minus I. So these blocks over here make up N plus P, minus 1 minus P plus I. Okay, simplifying this is N minus I minus 1 blocks to start and P plus I to end. These blocks, these N minus I minus 1 blocks can be tiled any which way. We said nothing about them. So how many ways are there to tile these? Well, Fn minus I minus 1, or N minus I minus 1 blocks, there are Fn minus I ways to tile these, right? That's what the theorem says. Our theorem says Fn is the number of ways to tile n minus 1 blocks. So n minus I minus 1 blocks could be tiled in Fn minus I ways. You follow me? These remaining blocks are made up of I dominoes and P minus I monominos. Okay? And they could be in any order. So there's a total of P tiles, and we have to choose what locations the dominoes go in. There's P, choose I, ways to do this. So this is P, choose I. Okay, and these are independent of each other, since there's no overlap in the first N minus I minus 1 blocks and the final P plus I blocks. So the total is the product. And I could vary from 0 to P. Again, there's no overlap here. You just count how many of the final P tiles are dominoes, and that gives you your appropriate value of I. And so this corresponds to the sum. And so we have that Fn plus P is equal to, well, we sum over all the values of I, and then we do this product. P choose I, Fn minus I. And there you have it. A combinatorial identity that involves a sum. I know you all said you wanted to see a series, so I thought we'll do a combinatorial identity in a series. Pretty neat. Let me know what you think. If you have any questions, yeah, I'm happy to do more examples like this. All right, see you later. Bye-bye.